Okay, so ladies and gentlemen, welcome back. Welcome back from spring break. So let's go over a few things here. Remember where we left off? We were computing arc length using this formula. Is that true? I think that's what I remember. We're using this formula. But we want to actually look at x as a function of y, okay, where y goes from c to d. And of course, the exact same procedure. Here's what we're saying here now. They're giving you now x as a function of y. Here's that function. Okay, so you're given a curve. But now you're going from a y value being from at the lowest c and at the highest d. They still want to ask you about arc length, this value s or l, whatever you want to call it, right? Okay, so I think I said last time, I said at the very end, we're going to get back to these kind of questions. You know, I got to look at an example where x is a function of y, and you're going to find that arc length, where it's really the same formula. It's the exact same proof. But this time, if they give you x as a function of y, then you have to find dx dy, right? Which is really g prime y. It's the same exact formula with the same derivation. And that's why you'll see here, you know, you need this g prime y right in here. And you square it, you add 1. But this is with respect to y now, the y variable. Right here. And this is y goes from c to d. Okay? And, you know, and then this is the same equivalent formula, so you guys know. dx dy. So they can give you x as a function of y, where y goes from c to d, or y is a function of x, and, you know, x goes from a to b. Anyway, so let's take a look at an example here. Let's go back to arc length. Not that. So it's the same procedure, just a different variable. So, okay, we went through this. Let's go back here. All right, so let's look at this kind of an example now. Let me find one for you guys. In my notes, where x is a function of y, at least we have to give you that kind of an example. Here we go. Here's one. Okay, got one in my notes. So they say now x will be 1/8 y to the 4th 1 over 4y squared, and then y will be between 1 and 2. Okay? They want us to determine the arc length. So, all right, here's going to be a complete example of what we're talking about. So, ladies and gentlemen, let me actually go to Desmos here if I can find it, so you guys can see what that looks like. So, x, and I already don't like the color. Okay, so x equals 1/8 y to the 4th. So, okay. Now here's the curve it looks like. Double check. Oh, no, 1 over 4y squared. There we go. but we're going to have to restrict the domain. So y goes from 1 to 2. So let's restrict that domain here. Okay, 1 less than or equal to y less than or equal to the number 2 here. So, okay. So as you guys can see, that's kind of what they're talking about. So notice this. I'm going to put here y equals 1, y equals 2. And I'm going to bring that picture in like I've been doing that so you guys can see that. All right, so let's bring that picture in. Let's go to, I think that was called arc length, right? Add to existing note. There we go. Here. There it is. Okay, so that's kind of what we're talking about. They gave you x as a function of y. And y goes from 1 to 2. They still want you to find the length of that curve. So you're still going to use the same formula now here. Okay, so you say, what do I mean? I need x prime, which is really dx dy, right? So now differentiate the x function. Was that 1/8 y to the 4th plus 1 over 4y squared? Is that true? Right? Yes. Okay. This is my x prime, so let's find that derivative. 1/8 4y cubed minus, let me remind you guys, this is 1/4 y to the -2 power. So put -2y to the -3, taking that derivative. So double check if we're okay with that, right? Yeah. Oh, I'm sorry. Let me get this out of the way for you guys. Okay, there we go. All right, so this looks like it's going to be 4/8, 1/2 y cubed minus, that's really plus, I think, plus 1 over 2 y cubed. Okay. And I think that's going to be, hold on, a minus. Is that true? It's a minus. There you go. Now, remember what we're supposed to do. We're supposed to take this, we're supposed to square it, we're supposed to add 1 to it, and then take the square root, right? So we have 1 plus 1/2 y cubed minus 1 over 2 y cubed. That's the derivative we're supposed to square. And of course, we have to take the square root, but I won't put it there yet. Now, notice what this does. It's going to give you that same pattern that we seen before the break. Okay, so let me kind of move this out of the way and do a little bit of the algebra. So remember, what do you have to use here? You're going to have to use FOIL here. So you get 1/4 y to the 6th for the first term, and then the outer term, right? What do we get here? Outer term, you're going to get 1/4, and it's going to be minus. think it's going to be minus 1/4. And then the inner term, another minus 1/4. And then the last term plus 1/4 y to the 6. So you get 1 minus 1/4 minus 1/4. What do you guys get? What is that going to be? I think that's going to be what? Change this to what? 4/4, right? So you get now what? 2/4. So I think that's going to be, is that 1/2? Plus 1/4 y to the 6 plus 1/4 y to the 6. Now I'm going to put that 1/2 right in here. Right in the middle. And I do that for a very good reason. Okay, because if you were to factor this, by the way, this would be 1/2 y cubed plus 1/2y cubed. Okay, so notice that. If you were to factor that, it's the same thing, but let's look at the details here. But it's a perfect square, trinomial, perfect square. Right in here. This is what I'm saying. You factored this right here. So it's very similar to what you see here. Because when you multiply that out, remember this is minus 1/4 minus 1/4. That's minus 1/2 right in here. So I just want you guys to compare and contrast. That's where we're seeing that exact pattern. Okay, the same exact pattern here. And now, remember, you're supposed to take the square root because this is all square root. So you're going to see that same thing happening again. Like I said, these are all specially chosen. And then what that means is this is the absolute value of what? 1/2 cubed plus 1/2y cubed. Now, remember, what's y? Y goes from 1 to what? 2. Is that right? So since y goes from 1 to 2, what that means is this thing is positive. So I can get rid of my absolute value, and that's the whole idea. Right? So this exact pattern shows up again if they give you x as a function of y, just like y as a function of x. So now that arc length formula, this is from y goes from 1 to 2, square root now of 1 plus x prime squared dy. Y goes from 1 to 2, 1/2 y cubed plus 1/2y cubed. This is your dy. Here's your arc length. Okay, so this is like the very last example I gave you guys before we went on break, but this is just x as a function of y. I think, like I said, the observation you want to make is right in here. This product is the same, but notice the sign is negative. Okay, you get that negative 1/2. So when I see this positive version, you write it as really with the positive. This is what I'm saying. It's a perfect square, trinomial. And that's the definition of absolute value. It's always positive. So we now have something very nice and easy to integrate, ladies and gentlemen. All right. So now the integral, what do you get by integrating? Do you guys know? We're going to do what? This will be 1/4 over 4, right? 1/2. Remember, this is y to the -3, right? So if I add 1, y to the -2 over -2, evaluate that from y as 1 to 2. So I really get 1/8, looks like, y to the 4th minus 1/4. And that'll be y squared down there. Is that y squared? Okay. From 1 to 2. So this is going to be 1/8, 2 to the 4th, minus 1/4, 2 squared, minus now 1/8, 1/4, minus 1/4, 1 squared. So 1/8 of, what's 2 to the 4th? Isn't that 16? Minus 1/4 times 4/16. That's minus 1/8 plus, no, that's going to still be minus 1/4, but we're going to distribute. Okay, so this will be 2 minus 1/16 minus 1/8 plus 1/4, I guess. Okay, so the common denominator is 16. So I'm going to multiply this by 2, 4 over 1, 16 it looks like. So this is going to give us 32/16 minus 1/16 minus 2/16 plus 4/16. (36/16 minus 3/16), that's 33/16. Anyway, here's your arc length. Okay, you guys okay with that one? So that's kind of, again, that's when you're dealing with x as a function of y for arc length. Anyway, okay. All right, so here's what I want to look at for you guys now today. So you're welcome back. So if you look at the title of this lecture, it's surface area. And so what I'm going to do here is go over the proof I've done. And this is going to be, if I go back to the website, by the way. Let's do that. Let's go to the website. Go to the browser. That's not for you guys. Go to Calculus 2. No, I want to go to this online transition. Should have had this, called it notes or something, but anyway, okay. Here's a surface area set of notes that I'm going to use for you guys because it's related to arc length. So the reason I want to go over that is it's related to what we're doing here. Okay, this is surface area for a solid of revolution. So go back. I actually have this in the iPad. So, you know, when they say solid of revolution, what does that actually mean? You guys remember? From Calculus 1. What does it mean when you have a solid? It says solid of revolution. Do you guys remember this from Calculus 1? What does that mean? We're going to start by taking a curve like this. Y is f of x. So here's a solid, by the way. And then you have to rotate this about the x or y axis. So you take a curve and you rotate about the x-axis or the y-axis. And this is generally associated with volume, if you guys remember the volume questions. This is what I'm talking about. So let me go back to go back again. Because you go, oh, Mr. Judge, what are you talking about? Yeah. If you go back to Calculus 1, let's go here. This is why they call it Calculus 2. Go all the way down here. Some of you guys remember, oh, what is this? Volume by the disc washer method. Volume by cylindrical shells, ladies and gentlemen. This is where we get that solid of revolution, taking a curve and rotating it. So if you need to go take a look at that, I'll put that also in the chat there. Okay, so this is when you take a curve and you rotate that curve. It's really going to be a region, and you rotate about the x-axis or y-axis. You create what's called a solid, and in that solid you get the volume, and that was in Calculus 1, the first course, right? And also down here you have the method of cylindrical shells to get the volume. So 2 methods from Calculus 1. This is kind of related. They're not going to ask you for volume now. In Calculus 2, they don't ask volume, but here's your formulas. In Calculus 2, ladies and gentlemen, they ask for a what? Surface area. So you're going to take a curve again, but now we don't want volume. That's Calculus 1. We want surface area. But you have to understand what is the surface area? What is it by definition, right? All right, so okay, we start with a continuous curve. Like always, y is a function of x over an interval AB, right? So here is that function, but it's over that interval AB. So I'm going to go with how they, this is x is A to x is B here. Okay? So here's how we start. We say, okay, x is A to B, like always. Here's your function. So you're really focusing on this portion of the curve. That's all. And what I've done is I've essentially given you a way. Here's really a formula for surface area. It's 2 pi r ds. 2 pi r ds now. Okay? And this is what's it's related to your arc length. So here's our surface area formula, but we're going to see where it comes from and we're going to see how to use it. Okay? So we want to know, where does this formula come from and how we can use it. Well, remember, you take this portion of the curve. Remember, S is this distance here. Is that true? That's the arc length. That's S. So when they say take this curve, we're going to start by rotating it really about the x-axis. So you're going to rotate that curve really about the x-axis, S. And that's exactly what I just talked about. And so what you guys see when you rotate that curve from x is A to B about the x-axis, I want you guys to understand something that you just did. You created here, this isn't a solid. Okay, I want to remark about that. That's an important detail. This is not a solid. You rotated a curve here. Right, a portion of that curve. You rotated that line, and what you create here is really, it's really describing the surface area. It's not solid. But if we look at the details again, to partition the x-axis into n subintervals of equal length delta x, that whole partition and idea. This is really the details here. Right? You're going to always focus on this ith subinterval here. And so you got P1, you got P2. This is that small delta S the distance from P1 to Pi minus 1 to Pi. So we always focus on that ith subinterval. And like I said, when you rotate this piece about the x-axis, you create this thing kind of like what it's called like a sleeve. This is not a solid. This is a surface area, like a side surface area. Not the surface area of the left or right side, but something that looks like this here. What do I have here? Yeah, I'm just doing the same thing. Just trying to communicate to you guys that we are focusing on what that did for us. That delta S, that small increment from Pi minus 1 to Pi, gives you this picture here that's shaded for the ith subinterval. This is what I'm saying. It looks like what we call a sieve, which means, this resembles a coffee cup sieve that is used to keep your hands from getting burned. So this is what I'm saying. This is like kind of that point, although it's oriented differently. You're taking this portion and you rotate it about an axis to give you this, what we're seeing there. That's what I'm communicating right here. Okay, but it's a different side. You have to turn the coffee cup. If I had to do this over again, I'd turn the coffee cup on the side so you can see it better. So it's oriented on the side. This is like rotating this. This is the axis that they're talking about here. Really that x-axis that you rotated. That's what I'm referring. It doesn't give you the area from the right or the left, just the side area. It's called the lateral surface area. Now, if you were to cut this, you're really looking at like a cylinder, the side of a cylinder. So that's all I'm saying is for a very small delta x and consequently small delta s, our conical shape resembles a cylindrical shape that can be cut along the side and create a rectangle. Well, ignoring the top and bottom of the cylinder, this is shown as the lateral side, the side of the cylinder. And how do you get the area? Well, the area of a rectangle is that length times width, which would be the circumference here of a circle. That's where you get 2 pi r. And then this length here. So the area is simply 2 pi rh, So what we found is the area for this I subinterval is 2 pi r really h. That's all this proof and demonstration is, 2 pi r h for that area. And so you might say, well, what am I saying here? Well, I'll go back and let's get some notation here where the R value, ladies and gentlemen, of that cylinder, this is your R value, by the way. Sometimes I'll call that Ri. You say, what is this? This is the radius here. For some Xi, that's your Ri. Okay? And so if we look at the geometry now all together, you might say, oh, I'm sorry, I did something here. This is not correct. This here, this distance here, for that value of what, for xi, okay, here's what I'm going to share with you guys. Your area is 2 pi r h here. So let's go back and do it again. This is your h. And for this is going to be your f of xi right here. Okay, see that point there? This distance? That is your radius. So Ri is really f of xi. That's the same distance. That's the radius of that circle. And then the depth is your h. That's delta s. So, okay. So now this makes a lot of sense now. Again, here's my radius value, Ri, if you want to think of it that way. And there's my height over here, h. So that the area is 2 pi r h, right in here. So if I add all of those approximate areas, I get this sum. This is approximation for the surface area. 2 pi r h. This is at Ri again. And my h is delta s. So what happens now is you take the limit. This is no longer approximate. This is exact. So the limit now over here, as n goes to infinity now, right? Your approximations get arbitrarily small. We obtain what's called the Riemann sum. This is your integral. So this is the exact surface area formula here, okay? So an important portion of the formula is to determine ds as your integrand. F of x is a function of x and is a different variable. So let's go through this idea here. Okay, so what I've proven here for you guys is that surface area is, this goes from x equals a to x equals b, 2 pi f of x. That's my r, and this is my h ds. This is ds. That's what I'm showing right here, but the devil is in the details here. Okay, so your y here is f of x. So you might say, okay, Mr. Judge, I got this here. Let me kind of emphasize what y is. Y is f of x. That goes right in here in your surface area formula. 2 pi, not f of x, or you could use f of x, or you can use y. But this detail about ds is new. It's not dx, it's not dy, it's ds, right? And you say, where does this ds come from? Right? This is my ds. R comes over here. It comes from, if I go back to the arc length portion here. Okay, let's go back to arc length. That arc length function that I'm giving you guys from those notes here, you know, all you did was fix an arbitrary x point for b from a, and you now have this arc length function here. So the fundamental theorem of calculus part 1 says ds dx. This is the definition of ds dx, which is the same as what you see here. So if I just solve for ds, my ds is defined to be the square root of 1 plus that y prime squared dx. This is that, you know, this is where you get that arc length function. This is your definition of ds. And then similarly, this is the same definition of ds. It just, you can have two. And these are called differentials, ladies and gentlemen, for your surface area. So go back over here, and you might say, is this why I just said our ds? Where's our ds at? Yeah, here's what we're talking about. Here's my ds portion. Here's the ds portion. So ultimately, r is your function here, f of x, or y. And this is, you know, you can now, since this goes from x equals a to x equals b, this is now a dx. You can now integrate. But this is the formula you have to use. This is your surface area formula. And what I actually gave you here similarly, if you said, what about if we take the curve x equals g of y from that we just did, y goes from c to d, what happens with our formula? Well, it's the same surface area formula, 2y ds. But you're going to have to use a different ds. They're the same. This ds now is going to be dx dy squared. And this is with respect to dy now. And these are y's here. So y goes from, oh, this is still going to be, I think that's a typo here. Looks like a typo. Yeah, it's supposed to be x equals g of y. So that means y goes from c to d. So this should be c to d. Let me get that here. All right, so y goes from c to d here. And if we rotate this about a different axis, we're going to have 2 pi r x ds. We're going to see how that works as well. Notice you have two different ds's. Here's what's going to happen. You got two different ds's, and you're going to have two different rotations. Y is about the x-axis, and here y is about the x-axis. So we're going to have to look at these examples here for surface area. See how that works. All right. Let's get this out. See how to use those formulas. So let's take out a whole bunch of examples here about how we can do this, because there's going to be some details to go over. Those will be some very important details. All right. So let's see some of these details here, ladies and gentlemen. I left my pen. So let's go back and let's call this surface area now. So let's do this here. All right, let's see here. We're going to say the following here. Your first example here of this, we're going to take y equals x cubed, okay, from 0 to 2. And you're going to rotate about the x axis. Now, again, just like for arc length, all these curves are very specially chosen. Don't just come up with a curve and try to rotate it any way you want and then integrate. If you do that, you're probably going to get something you can't integrate. These are all very specially chosen questions. Let me go to Desmos here to show you guys this. So y is x cubed now. So we'll say y is x cubed. And then what did x go from again? Do you guys know? So I'm going to restrict my domain, okay, from 0 to 2, because that's really what it is. 0 less than or equal to x less than or equal to 2. I guess that looks pretty good. Okay, let's bring that in so we can see how this works together. Okay, so here we go. Now, you're going to rotate this about the x-axis. Is that right? So you might say, well, what's the big deal there if you rotate it about the x-axis? Sorry, I didn't do all of this here. So let's rotate this about the x-axis. Here's your x-axis from 0 to 2. Okay. So you take the curve from 0 to 2, rotate it about the x-axis, and my curve isn't the best. But you're not creating a solid. You're creating, that curved portion in purple. All those points get rotated about the x-axis. And you're creating really, well, it's not a solid, but it's the outside. So you're looking at surface area. And you use the surface area formula. So automatically, you say this is integral 2 pi what? R ds. So automatically, you write down your formula. What you need to know is what is R. I guess I'll use purple. R is your radius. Is that true? So for some arbitrary x value in that interval, this is f of x. This is my radius. Okay? So we can say this is f of x or this is y. That's why in those formulas they have either f of x or y, because y equals f of x. You say, well, how do I know that? This is right up here. Y is f of x. So this is the radius. It's the function. Okay, easy peasy. Because that's the disk, that circle here, there's radius value. That's the disk. So you say, okay, here's my surface area. It goes from 0 to 2. Those are x values, right? X is 0, x is 2. 2 pi y f, I guess that's x cubed, right? Now, here's the second part you have to determine. This is an extremely important detail. Okay, so remember when I went back in the notes and I said to you, you got 2 here. This is what's important. I'm going to try to get rid of all this other stuff. Okay, get rid of that. Just so it doesn't distract us. We have 2 ds's. My first ds, my second ds. What's important for you guys to know is which ds do you use. You need to use the ds that's going to allow you to what? To integrate. Because in one case, ds is in terms of dx, and that's like right here, so it's going to be 1 plus y prime squared. The other case, your ds is in terms of what? The dy. So which one are you going to use here? You got choice 1 or choice 2. Which one's going to allow you to integrate with your variable, with the radius? Guess what you get to use here? Go back and take a look. What do I have? I have what? This is the variable x. So the ds you have to use is going to be what? The 1 where we have this dx over here. So this would be 1 plus what? Y prime squared. So that surface area is going to be from 0 to 2. This is my x variable. 2 pi x cubed square root 1 plus dy dx squared. And now I can integrate because that's dx. It's not ds anymore. So it's the dx. So that's what I want to share with you guys. You got 2 options for ds here. And now you know what y is, right? What is y? It's x cubed. What would y prime be? Right? I have to differentiate what? x cubed. And what is that? Isn't that 3x squared? Okay, so my surface area will be that integral from 0 to 2 pi x cubed square root 1 plus 3x squared squared dx. And I can pull out the constant 2 pi. And now, ladies and gentlemen, this is 1 plus what? Is that 9x to the 4th? Okay, dx. So here's what I want to remark again. I said it already, but remember what I said? Don't just put any function for y and rotate it any way you like. If you do that, you can head into some trouble. Meaning, what you get, you may not be able to integrate. This one, you can. How do you guys integrate this? Do you guys know? What do you guys think? How do you guys integrate that? What technique do you guys use to integrate this? It's very easy. This is kind of like a calculus 1 integral question. Why do I say calculus 1? What do you guys use? Don't you use u sub? What is u? 1 plus 9x to the what? 4th. Right? Isn't this your u right up in here? You see what I'm saying? There's your u. It's a calculus 1 question. So du dx, what's that derivative? Isn't that going to be 36x cubed? Where dx becomes what? Du over what? 36x cubed. Don't forget, this is x is 0. This is x is 2. Don't we have to change that to u? Right? You guys know what I'm saying? Because you got your x cubed going away. So if x is 0, what does u become? Isn't that 1? If x is 2, what does u become? 2 to the 4th times 9. Isn't that 2 times 2? 4. Is that 16 times 9 plus 1, I think? Okay, 16 times 9 plus 1. What is that? $145? Right? Because we're going to use this to change our limits right up in here. All right. Two pi, we go from u equals 1, u equals 145. And that's going to be u to the 1/2 over 36 du. So we get pi over 18 if I pull that out, constant. U is 1. So I'm just going to put the 1 and the 145. U to the 1/2 du. This is a straightforward u sub question. And then that's going to be what? What is this going to be? Isn't that u to the what? 3/2 divided by 3/2. Don't forget that factor of pi over 18 from 1 to 145, which is going to be pi over 18, right? Times 2/3 u to the 3/2 from 1 to 145. Pi over 27 u to the 3/2 from 1 to 145. So we get pi over 27, 145 to the 3/2 minus 1 to the 3/2, which is going to be pi over 27, 145 square root 145 minus 1. So it looks like that's our final answer, ladies and gentlemen. Right? Because what I did was I simplified the 145 to the 3/2 power in the way I showed you guys. I don't know why it doesn't want to draw an ellipse. There we go. So that's your surface area. Notice that's a nice positive number, but you just computed your first surface area, ladies and gentlemen, using the surface area formula. Okay, so this is how you handle, they give you y as a function of x. I want you guys to note here, something to really note. Y is a function of x, and you rotate it about the x-axis. Because you want to compare and contrast this next situation, right? I want you guys to compare and contrast this situation here, this example. They give you y equals x squared from 0 to the square root of 2, a nice parabola, but they now want you to rotate not about the what? X-axis, to rotate about the what? The x-axis. So compare and contrast. This is going to be rotation about the what? That's the x-axis. Sorry. This is going to be rotated about the y-axis now. Sorry. So this is a compare and contrast situation. Okay, rotate this about the y-axis now. The first one is about the x-axis. You're given this. You're going to see how this works. Okay, so let's go to Desmos. I know you guys know what a parabola looks like, but compare and contrast here. 0. There it is. Okay, you guys okay with this here? So this is what you're looking at. And now they want you to rotate this about the what? The y-axis instead. So when you do that, notice what happens with your curve, right? Not the best artist. Sorry. You take that curve I want to do an ellipse. No, I don't want to do that. Ellipse. Whatever. It's weird. Yeah, whatever. Okay, we're going to keep it like that as straight. So we're taking this curve again, and you're rotating it, so you're creating this surface area here. Now, remember, what's your surface area formula? This is the key. It's 2 pi r ds. Now, you created here in this picture a disk. So the question is going to be, what's this radius value? Do you guys know what radius is? Oh, how do we get this radius? You guys know what the radius here is going to be? It's going to be just, isn't that going to be just x? Right? So if I said to you guys, let me see if I can draw this. I'm going to draw this picture here. This is my ds, right? But then what is the radius here? That distance, ladies and gentlemen, here is your arbitrary x value, right? Between 0 and the square root of 2. So the distance, what I'm trying to say here for you guys is that radius, this horizontal distance is just x. So in this case, the radius is x. It's a horizontal distance. Here, compare and contrast. Your radius is what? It's this vertical distance. This is the same distance here, vertical. That's f of x. So here your radius is f of x for that vertical distance, for the radius of that disk. Here, the radius is what? Is the x value. Now that's important because that goes right in here. There's an x there. So the question now becomes, what ds do we need if that radius is x? It's not f of x. The radius is just x. What's our ds? It's going to be the one that gives me what? Let's do an arrow here. So the ds now, again, has to be the one that gives you a what? Has that dx. Because you have to integrate this. And here, yes, x goes from 0 to what? Square root of 2. So in this case here, you got to be careful. Even though you're rotating about the y-axis, that radius there is the x value. And then this is going to be y plus, again, 1 plus y prime squared. Since y is, you say, what is y? X squared. I can get y prime easily. Y prime would be what? 2x. Is that right? So 1 plus 2x squared is 1 plus 4x squared. And that's under the radical. Altogether, ladies and gentlemen, that surface area formula is going to give you, integrate from 0 to the square root of 2. That's an x value. 2 pi x square root 1 plus 4x squared dx. Because that ds has to have the dx if you're going to integrate. Your radius is the x value. The radius is not f of x. The radius is actually a horizontal distance, not a vertical distance. And again, what do you guys use to integrate? This is now, what kind of question is this? This is now u sub, where u is 1 plus 4x squared. Okay, so by u sub du dx is 8x, or dx is du over what? 8x, right? So by u sub, and don't forget to change your limits. The lower limit is 1. The upper limit is going to be 17. Is that true? Double check. How did I get these new limits? Right? This is an x value. Plug it in here. When x is 0, it doesn't matter if it's being squared and then multiplied by 4. So that'll be a 1. Then plug in x as the square root of 2. Well, square root of 2 squared is 2. 2 times 4 is 8. 8 plus 1 is 9. So sorry, that's going to be a 9. I guess I better wake up. All right. I can integrate. So my surface area is going to be now from 1 to 9. 2 pi x square root of u, and then dx was what? Where's our dx? I'm sorry. It's du over that 8x. Yes, we didn't actually solve for dx. Now we did. Okay. So 2 over 8 looks like it's going to be pi over 4. We integrate from 1 to 9. E to the 1/2 du. And again, it's the same. Double check to see if my work's fine. E to the 3/2 over 3/2. 1 to 9. Pi over 4. 2/3. 1 to 9. Looks like this will be pi over 6. 9 to the 3/2 minus 1 to the 3/2. Now, 9 to the 3/2, ladies and gentlemen, going back to intermediate algebra, 9 to the 3/2, that's the square root of 9, which is 3, 3 cubed, 27 minus 1. Looks like it's pi over 6, 26. Double check. Is that 13 pi over 3? 2 goes into 26. How many times? 13. 2 goes into 6 3 times. So double check, ladies and gentlemen. I'm not awake. 13 pi over 3. And that's what I've gotten before. So ladies and gentlemen, I want you guys to compare and contrast these two different examples. Okay? Because this is kind of going to be the big deal. This is where you get y as a function of x, and then you rotate it about 2 different axes. Notice I have to change the function. I can't use the same function. If I did, I might get something I can't integrate by u sub or anything. So it's like you're saying, well, why did you change the function and you rotate it differently? So I can integrate. You know, and then again, if you did this sort of, I should say to you guys, let's say you did this in a way that's random, right? Well, then you'd have to use a numerical technique to integrate. All in theory. You'd have to use numerical techniques like Simpson's rule. So sometimes even in the homework, they might say set it up, but don't integrate. The reason they say don't integrate is because you can't integrate it. That's the reason. And then sometimes they'll say, hey, use Simpson's rule. But if they tell you just to generate arc length, determine that, and they give you a function, they tell you how to rotate it over an interval, it's integrable. You should be able to integrate it. So there's 3 situations. You say, what are the 3? Well, when you can integrate, and they just tell you, find the arc length. When you can't integrate, they're going to say one of 2 things. They're going to say, just set it up, or they'll be more specific, and they'll say, use Simpson's rule to numerically, integrate this. So those are really the 3 situations over arc length and surface area. Because again, you can only integrate just so many things, really. It's very limited integration techniques. It doesn't seem like it when you first study it. Seems like, wow, you worked with a lot of integrals, and you have. But there's more things that you can integrate than what you can. It's a lot more. It's a very, very interesting idea. But anyway, that's how you start surface area. And so tomorrow, I could give you a couple more examples, which I wanted to do. I don't know if we have time. But ladies and gentlemen, I apologize for the late start today, but I was in a quick little meeting here. And let me get rid of some of these things here. Okay. Here we go. All right, ladies and gentlemen, here's the deal. What did we do yesterday? Do you guys remember? We had this surface area formula, 2 pi r ds. Okay? Now, and I also want you guys to know that we have 2 ds's here. Square root of 1 plus y prime squared, okay? And that's dx. We got ds will be square root of 1 plus x prime squared. And then that's dy. Now, this is the 2 types of ds. All right, you guys okay with that? And the key here is to note a few things here when you rotate. So yesterday, I'm going to put some notes. See if you guys recall. In both cases, you had y as f of x. Is that right? And then how did you guys rotate yesterday? First, we started off by rotating about the x-axis. Is that right? Then I have y as f of x here. And then you want to rotate about the what? Y-axis. So, all right. Two different rotations from yesterday. And so the key is going to be, remember, you're going to find, what's your radius? You guys remember? You have your radius value. So you want to find the radius. And you want to use the appropriate ds. So, all right. So if I go all the way back here from yesterday, and you said, okay, here's my first situation. You rotate about the x-axis, y as a function of x. And that radius is right here. The radius is actually the y value. So when you rotate about the x-axis, let's summarize what we did. Your radius becomes that y value. Is that right? So here, the radius is the y value. And the y value happened to be what? F of x. So I'm just wanting to let you guys know, here's my radius. And then what happened when I rotated about the y-axis? Go back over here. What happened with your radius? It's now going to be the what? The x value. So your radius is the x value here. So I just want to summarize this here for you guys, okay? So if I look at another quick example, because I remember I said you guys, I wanted to do another one or two, and yes, you guys have that video there. Let's do something like this. Which one did we do? Yeah, I don't think we did this one, right? Did we do this one here? See if you guys remember. Y is 1 minus x squared. Here's your curve. And then 0 to 1. Okay. And then you want to rotate about the what? The y-axis here. Okay, so I'm going to look at this quick example here. And of course, I'm going to go out to Desmos again. Y equals 1 minus x squared. Okay, and then we're going to do, you guys know I like to change that color. 0 to 1. Parentheses 0 to 1. Okay. So we're going to go into that existing node of surface area. Okay, so here we go now. So let's take a look at this and see if this makes any sense, right? How are we going to rotate here? We're going to rotate this about the y-axis. Is that right? Now, when you rotate that curve about the y-axis, notice what you get here. Okay, and this is what we're looking at. So our radius here, let's double check. that radius, what's that radius going to be here? Right? The radius is the x value, just like we just said here. So here's our radius. And then let's do orange. Rotate about the x-axis. Rotate about the y-axis here, right? So this is a y-axis. So sure enough, our radius is x. And that's the whole idea. So that when your surface area formula, you say, here's my surface area formula, right? Surface area is going to be that integral 2 pi r ds. So we know that radius, again, like we said here, is x. So this portion here is going to be just x. So far we get surface area integral 2 pi x, and then this is going to be a nice ds. ds. So how does that look, ladies and gentlemen? How does this look here? This ds. Which ds do I get to use? The one that ends with dx. Why? Because it allows you to integrate. Good job. So remember, that's 1 plus y prime squared now. So yes, that's how you want to approach this here. Surface area. 2 pi x, this will be 1 plus y prime squared dx. So remember, what is y here? Y is that 1 minus x squared. Okay? You guys see that there? That means y prime is minus 2x. So then 1 plus y prime squared, what does that become? 1 plus minus 2x squared, which is 1 plus 4x squared. But don't forget, you have to have the square root. Okay? So that goes right in here. That's going to be your 1 plus what? 4x squared, and this will be dx. Okay, you guys okay with that? So here's your surface area. 2 pi x square root 1 plus 4x squared, and then that's going to be our dx. Now, what does that x go from? 0 to what? 0 to 1. So what do you think this is going to give you guys when you integrate this? Right? What do you guys get here? Right? What do you guys get now? How do you guys integrate this? You're going to have to use what? U sub. Isn't that your u right in here? So this becomes du dx. What's that derivative? Isn't that going to be 8x? Okay, by u sub, and that means my dx is going to be du over 8x. So let that be known. If x is 0, what is u going to be? Isn't u 1? Because we have to change the limits as well. So if x is going to be now what? 1, what is u going to be here? 1 plus 4 is what? 5. So dx will be du over 8x. Okay, so you get to cancel that x. So pull out your constants. 2 pi over 8, we integrate from 1 to 5, u to the 1/2 du, pi over 4. You get now u to the what? 3 halves over 3 halves. We evaluate this from u as 1 to 5. Pi over 4 times 2/3. U to the 3 halves. 1, 5. Pi over 6. 5 to the 3 halves minus pi over 6. 1 to the 3 halves. So we could just write it as pi over 6, 5 square root of 5 minus 1. And so, ladies and gentlemen, there you go. And there it is, ladies and gentlemen. So this is the additional example I wanted to do. There's more, but, you know, anyway. Okay, so what do you guys think about that one? Is that okay? Let's see if I can find some interesting examples there. So there we go. Kind of odd. Okay. Here we go. Another example. Let's get an example in the book. How's that? Let me see if I can get one. This is on 9.2. Let's get a surface area. I think it's 9.2. All right, let's do this here. X equals 1 plus 2y squared, and y goes from 1 to 2. Yeah. And you're going to rotate about the x-axis. All right, so, all right, let's double check here. Now I'm going to go to Desmos to share with you guys more of the pictures. So x equals 1 plus 2y squared. And what was y going through again? What was that interval? 1 less than or equal to y, less than or equal to 2 here. Okay. All right. So let's try to get this here. It's kind of odd. I do existing now surface area here. Where'd it go? Let's try that again. So you want to rotate this about the what? About the x-axis. So if you do that, you get, you got a curve like this, and I guess it's not a line, right? X plus, it's really not a line, but okay. But let's see, this is what I mean by that. You're going to have this kind of shape here. Okay. And again, you might say, okay, what's our radius here? Right? You guys know what a radius is going to be now again? Right? Your radius is going to be what? Isn't it going to be a y value? How do you get the radius? What's that distance? Anybody know? What's our radius going to be here? Right? You want to use a variable. Is it y or x? Radius is your y value. Is that true? It's that value of y. It's the height here. So notice what they gave you in this case here again. They give you x now as a function of y. You're going to rotate this about the x-axis, so your radius is a y value. Surface area, 2 pi r ds. Is that true? And what did you guys just get through saying about the radius value? Your radius is y. Is that right? So you say, okay, 2 pi y, we have a ds, but what is y going to go through from 1 to 2? Is that true? So y goes from 1 to 2. This is a y value, so I want to emphasize that for you guys. Surface area is y is 1 to 2. And so here's the ds here. So which ds are you guys going to use? One that gives you the dy, is that right? Because you have to integrate with that. And this will be, this then is 1 plus what? What is this? X prime squared. That'll give you the dy. So remember this ds here. When you want that dy, this has to be an x prime squared here. Okay, you guys okay with that? And that's kind of a good thing. Why is that a good thing? Right? Oops, I'm sorry. Sorry, let me get that here. What's x prime? You guys see what this is? if x is 1 plus 2y squared, what's x prime? Isn't that 4y? So you get 1 plus what? 4y squared. Square root 1 plus 16y squared. Y is 1 to 2, and then you have what? 2 pi y square root 1 plus 16y squared, and then this will be a dy. And what do you guys notice about this one here? What do you guys notice in this case? Anybody notice anything about this? Again, what do you guys notice? Isn't that a u sub question? This is u. So u is going to equal what? U is 1 plus 16y squared. So then du dy is going to be what? 32y. Or we say, what is dy? Du over 32y. Is that right? We got u sub. What do you guys notice? We're going to have to change our limits. So to change our limits now, what do we get here? If y is 1, what is u going to be? 17. Good. Now, if y is 2, what is u going to be? 1 plus, what is 2? Is 2 squared 4? What's 4 times 16? Yeah, that'll be 65. Okay, good. Get rid of your y's, and you get what? 2 pi over 32, 17 to 65, u to the 1/2 du. So this would be pi over 16, 17 to 65, u to the 1/2 du. So this is u to the what? 3/2 over 3/2, 17 to 65. So what do you get now here? Pi over 16 times what? 2/3. U to the 3/2, u is 17 to 65. This is going to be 8, so it's going to be pi over 24. U to the 3/2, 17 to 65. So, ladies and gentlemen, you get pi over 24, 65 to the 3/2 minus, I guess, pi over 24 again, 17 to the 3/2. You can factor out the pi over 24. And now you get really 65 square root of 65 minus 17 square root of 17. And there you go. There it is. There you are, ladies and gentlemen. Easy peasy, lemon what? Squeezy. So, yeah, okay. I think I understand what you're saying. You're saying something like this, right? You're saying, can you just say solve for y here? I would not recommend it. And you say, well, why would I not recommend it? I mean, you might be able to, you're going to have to remember that you're going to get two kinds of y values because this is a, you get two y's, right? If you solve for y, you got y squared, you got plus or minus. And if you did that, right, so here's kind of the remark. You might be tempted. So let's do this as a note, right? So you said x, what is x going to be? 1 plus 2y squared, right? You got x over 1 over 2 is y squared here, which means y will be plus or minus square root. Okay, now you get two answers here. It's one's positive, one's going to be negative. Now, if you look back at the curve here, you say, well, where's the curve? This is our curve. The y value was positive, so in other words, that's why I took only the positive square root. Because the y coordinate values above the x-axis are all positive. So you can do that in theory, and then you have to change your limits. But remember what's going to happen. Eventually, you're going to have to integrate a function. And so if you said, I want to write this all in terms of x now and do that, you might have a real issue with how to integrate. Because you need to get the, probably a y prime here. You got to find that derivative. You got to square it. You got to add 1. You take the square root. So the reason I would say I don't recommend that for this kind of question is because you can get in trouble with trying to integrate. And so in theory, it can be done, but then you'd probably have to do a numerical approach, and that's not what they want. They want you to get the exact value. So sometimes I guess the better phrase can be, give me the exact value. You know what I mean? Yeah, so that's kind of why I would not recommend it. In other words, go with the function as x equals g of y, because it's going to it's going to give you a nice what? Here's my point. It's going to give you a nice u sub question. Okay, you guys okay with that one? And let's do, this is rotating about what again? This is rotating about the x-axis. Let's try to find a function where you rotate about the y-axis for x. So I'm going to try to make one up here. X equals, I'll say this, square root, maybe 1 minus y squared. 0 less than or equal to y less than or equal to 1/2. Rotate about the y-axis. Okay, so let's go back here and say, let's put this in Desmos and say, what do we have now? We have x equals what? Square root 1 minus y squared. And I think we said, what? Let's do the restricted domain again. We have 0 less than or equal to y less than or equal to 1/2. It's kind of weird. What happened? There we go. Let's get rid of this. And this is rotated about the y-axis, right? So, okay. All right, so when we rotate this about the y-axis, what happens now? Don't we get something that kind of looks like this? Let's see if we can figure that part out, right? All right, this is kind of like if you guys remember working with volume. Calculus 1, okay? Working with some volume here. So what would you guys say what is our radius now? I don't know. Let's see. Is your radius going to be x, ladies and gentlemen? Let's see. What was this here? Your radius here, when it's vertical, radius is y. Horizontal, radius is x. Is that right? So when you look at this picture, surface area is going to be integral 2 pi r ds, where this is going to be, right? You say your radius is going to be what now? Is your radius x? Okay. So this radius is what? X. Is that true? Okay. But what do you guys notice about this question here? How is this one different? What does x equal? X is the square root of what? 1 minus y squared. So you can replace this here with the what? Square root. 1 minus y squared. And then what's your ds? What do you think ds will be? Well, let's see. How are you going to integrate? Remember, they gave you y goes from 0 to what here? 0 to 1/2. And what's your ds? Which one are you gonna use? One that has what? dy. You say y. So you can integrate, right? So this is gonna be 1 plus what? X prime squared. So if x is square root 1 plus y squared, which will be, and that's in the square root, minus y squared to the 1/2. Here's my x. What is x going to be here? What is x prime going to be now? 1/2. 1 minus y squared to the minus 1/2. And don't forget to differentiate with respect to y by chain rule, what you guys see here. So by chain rule, this is minus 2y. So x prime becomes 1/2 1 minus y squared to the minus 1/2 times a minus 2y. Minus y over the square root of what? 1 minus y squared. Double check. Are we okay with that? So notice what happens here. Because they give you x equals g of y, you have to use that. And that's how it's different. So this is why I want to go through some of these kind of examples here so you guys can see that there. So now we put the 1 here plus what? This is y squared over 1 minus y squared. 1 minus y squared plus y squared over 1 minus y squared. 1 plus x prime squared. Okay? And that was actually with the square root, so let's go back. Okay. No, was it? No, there we go. So we have to do the square root. No, it's okay. We're good. We're good. Yeah, no, we're good. 0 to 1/2 is fine. Yeah, okay. So now you say, okay, that's my radical. Now take a look at what this is going to give you, right? So let's write down the surface area here. What is that going to give us? We're going to integrate from what? What is that going to be? 0 to 1/2, right? Two pi what? Remember this x, square root of 1 minus y squared. So this is going to be here. What is the square root? 1 minus y squared. Is that true? And then, what do we have here? What's our ds? Would you be able for the ds, Professor, to drop the square root? Well, let's put the ds in here. So let's put this ds here, right? This is 1 over what? 1 minus y squared, and this is going to be a dy, is that right? This is dy. What do you guys notice you get? 0, 1/2. Do you guys know what you get? Doesn't this cancel? Is that right? And so what's your surface area going to be? Isn't that 2 pi y from 0 to 1/2? What's that going to be? Two pi times 1/2 minus 2 pi times what? 0. What's the surface area going to be? Pi. And there it is. Surface area is going to be pi. Okay, so let's kind of go back and do a little bit of a summary here. You go, what do you mean a little bit of summary here? Notice what happens here, because I think I might have wrote in that in the notes. So if I note, let's do this here. Let's do a nice summary for you guys as well. Right, so if I want to summarize this, let's give you guys a note here. X equals g of y. X equals g of y. If you rotate about the x-axis, you rotate about the what? Y-axis. What's your radius going to be here? The radius is y. What's your radius over here? X. Was that true? Let's go back and double check. Rotated about the y-axis. What was the radius? X. Rotate about the x-axis. What's your radius? Y. Okay, you guys okay with that one? Another example. Let's see if I can find one here. Okay, let's do something like this here. What's the remaining time? We may not be able to finish this, but okay. I'm going to give you guys something like this, okay? X squared over 9, y squared over 4 equals 1. Is rotated about the x-axis. Well, let's see. What are they talking about here? And all they said, this is kind of what they give you. But what I want to remind you guys is this. What are you guys looking at? What are you guys looking at? Do you guys know what this is? This is an ellipse. And so when you rotate an ellipse this way, you create what's called an ellipsoid. Okay, so you're looking at this here. You go, oh my God, what are they doing? They're rotating an ellipse about the x-axis. So what you create is what's called an ellipsoid. It's a 3-dimension. It kind of says, you kind of look at this, you go, is that a football? I don't know, is that a football? Maybe. So here's what I want to share with you guys. Two, 3, -3. Okay. So how you want to do this is this way. And I know you're gonna rotate this. You say, but isn't this going to be my ellipse? Well, this is how you guys approach this question here. How do you get the top half of this equation here? Do you guys know? This is where the y values are positive here. You're going to have to solve this for y. Okay, so you solve this for y. So you might say y squared over 4 is 1 minus x squared over what? 9. Which means y squared is going to be 4 times 1 minus x squared over what? 9. Okay? So y squared now is going to be 4 times 9 over 9 minus x squared over 9. We're solving for y. So y squared is going to be actually 4/9. 9 minus x squared. So what does that mean about y then? Y is going to be what? Plus or minus square root of 4/9. 9 minus x squared. Now what do we just get through saying? It's going to be positive. Okay? 4/9. 9 minus x squared. So what's this going to be now for y? This will be what? 2/3. Square root of 9 minus x squared here. So you're going to rotate this about the what? about the x-axis, right? So if you do, right, remember this, what's your radius going to be? Right, you guys know what your radius is? What's your radius? Radius is y, is that true? Okay, so you got the surface area formula here, which is going to be what? The integral 2 pi r ds, and this goes from, I think it's -3 to 3, is that right? So what was our radius again? Y. Okay, your radius is y. That's what we got through saying. But what does y equal? Y is 2/3 right here. So here's your surface area. 2 pi 2/3 square root 9 minus x squared. What is this? This is a ds. What is that ds? You're going to need to have what here? Square root of 1 plus what? Don't you have to have that? Is it x prime? Doesn't that have to be a ds? So this is what? Y prime squared. And so now, again, that makes sense because x is from -3 to +3 right up here in your picture. So it makes a lot of sense here. And moreover, we could make this really simple by saying what here? This is 8 pi over 3. Why did I double that and change my limits? Do you guys know? Isn't that an even function over a symmetric interval? So an even function over a symmetric interval, I'm just going to deal with that limit of 0 better. I don't have to, but I have to double that. Remember that? So I have to double the area. But you have some algebra to do or some calculus to do. So what was y again? Remember this, y is going to be, what's our y function? 2/3 square root 9 minus x squared. So y prime becomes 2/3 1/2 9 minus x squared to the minus 1/2 times a -2x by chain rule. Is that true? So it's going to be what? It's going to be negative. The 2's will cancel. Is that right? Net 2x 3 square root 9 minus x squared. Double check. Now, square that. So that's going to be positive 4x squared over what? 9 times 9 minus x squared? Is that true? Now you have to do 1 plus what? Y prime squared. So it would be 1 plus 4x squared 9 minus x squared. So you're going to have same denominator. 9 minus x squared over 9 minus x squared plus 4x squared over 9 minus x squared. Okay? And now what happens here? That 81 minus 9x squared, is that plus 4x squared? 81, something's bothering me about this. Here's y. Okay, we got y there. Okay. Anyway, what's that? 91 minus what? 5x squared over what? 9 times 9 minus x squared, I guess. So double check to see if we're okay. It looks like we are. So we end up with square root 81 minus 5x squared over 3 square root 9 minus x squared. Okay? So that is what we're going to have to put where? See this here? Maybe I should have kept it in red. That goes right in here. So let's do this here. 8 pi over 3, is that right? Integral 0 to 3 square root 81 minus 5x squared over let me go back here. What was that original? Let's put it in order. I don't want to switch the order on you. Square root of 9 minus x squared. Okay? And this goes away. So it looks like we get 8 pi over what? 9. We're going to integrate from 0 to 3. Square root. Is that 81 minus 5x squared dx? Double check. Double check, ladies and gentlemen. Hopefully we did not make a what? Mistake somewhere? So how would you guys integrate this? What do you think? How would you integrate this? What would you do? A u sub? And that's not from 3 to 3. What would you guys do here? There's a couple of things I think you can do. Here's 2 things you can do. Use a trig substitution maybe? Or is there a formula here? Is there a formula for something like that? And if you had to use a formula for something like that, that really now becomes a u sub. Is that right? So it's really a u sub and maybe a formula for something like that. U sub and that. Okay. So just to let you guys know, I want you guys to try to look at that and see what you can do. Sorry for the late start. I was in a quick meeting, important meeting, and anyway, take a look at that. See how you can handle that. Is there a u sub formula for that one? Double check. Trig sub. You can at least do it by trig sub. Okay, folks, we'll see you guys tomorrow. Take care, stay safe. I hope you guys enjoyed some of these, but what I want to remark is this. This problem that we just did, or we were working on, forming what's called an ellipsoid, finding the volume and the area in we're going to see that again a little bit in the next section, I think, or the next chapter. No, maybe this section, this chapter. There's easier ways to integrate something like this to find area and volume. And in Calculus 3, you do this again in Calculus 3, but you do it with a double and triple integral. So you do have to know how to integrate to do the easier versions. In other words, there are easier approaches to what we just did here, but that requires you to have knowledge of how to integrate, both in Calculus 2 and Calculus 3 in our future. So what's the point? Know how to what? Integrate. And know how to differentiate, obviously. All right, okay, we'll see you guys tomorrow. Oh, and I'll pass back your exams tomorrow. I left them at home. As you guys know, they're graded. I even have the solutions online. You can check Canvas. But I'll pass that back for you guys tomorrow, that portion. So we'll see you guys later.